Next chapter is the particulate nature of matter. Now, in order to understand and be able to predict the behavior of substances, we need to understand their nature and composition. Matter is anything that has mass and occupies space. All matter can exist as either solid, liquid, or gas. These are called the three states of matter. In each of these stages, matter has different properties. Matter in solid state has a definite mass, volume, and shape. Liquids have definite mass and volume, but no definite shape. Gases have definite masses, but not volume nor shape. Now, here is the interesting thing, and which is the main interest of this chapter, that although different substances may have different forms and properties, they have one common feature, a particulate nature. In other words, all matter is made up of many tiny separate particles. Take a look at this piece of rock. Obviously, it broke off from an even larger rock. If you hit this rock, you can break it into smaller pieces. Hit these two and you get even smaller pieces. You can continue until you get to powder. If you can continue hitting and breaking it even further, you will at one point get small pieces, so small that you can't break them further. This points to a very simple logic, that this rock is in fact composed of very, very tiny particles that are assembled together. And believe me, even this drop of water is made up of similar small particles. It is the arrangement and behavior of these particles that give different substances their unique properties. In this chapter, we shall strive to understand the existence of these particles by looking at the various proofs that we encounter every day. But first, this concept of the particulate nature of matter has four postulates. 1. That matter is made up of many tiny individual particles. 2. That there are spaces in between the particles. 3. That the particles are in constant motion. And 4. That the particles attract each other. Let's start with the first one, that matter is made up of tiny particles. We take some 4 crystals of potassium permanganate and dissolve them in 100 ml of water. Then we take 10 milliliters of the solution and add it to 90 milliliters of water to make another 100 milliliters of solution. We do the successive dilutions 3 more times. You will see that the intensity of the color gradually decreases with each dilution. And this indicates that the 4 crystals contained millions of tiny particles that can be transferred from one solution to another, giving the water the pink color. Secondly, that there are spaces in between the particles. We can demonstrate this using salt dissolving in water. First, we note the level of water in the beaker. After stirring, all the solid salt disappears into the water, but the level of water doesn't change. If all matter occupies space, how comes the volume of the water did not increase? The reason is that by dissolving, the salt broke into its tiny particles which occupied the spaces between the particles of water. If these spaces were not present, then the volume of the water would increase. Thirdly, the particles are in a constant state of motion. Let's start with liquids. The first evidence that particles in matter are constantly in motion came from the study of pollen grains' behavior in liquid. In 1820, a botanist, Robert Brown, was carrying out a study on pollen grains. He decided to crush the pollen and suspend the grains in water. But when he viewed them, the pollen were continuously jetting around. We can also see this effect when looking at carbon particles. A drop of carbon powder suspended in oil is placed on a slide and viewed under a microscope. The carbon is seen to be bouncing around. This is called Brownian motion. This motion is caused by the grain and water particles colliding and bouncing off each other as they move around. The same is happening to the carbon and oil particles. Brownian motion can also be seen in gases. Smoke from a straw is injected into a smoke container. A lid is used to keep it in place, and a bright light enables it to be viewed under a microscope. It looks like tiny jittering points of light. When the straw burns, it produces mainly carbon particles which haven't completely combusted. Under a microscope, they cast the light and appear to glimmer. This dancing around of the carbon particles is caused by collisions with the invisible air particles. As the air particles move about, they knock the carbon particles randomly in different directions. So this is proof that the particles of matter are in constant motion. And so in conclusion, we say that matter is made up of tiny particles which are in a continuous state of motion. This is called the kinetic theory of matter. So let's look at the arrangement of these particles into three states of matter and see what makes them different. Particles in the solid state are closely packed together in a regular pattern and have very small spaces between them. The particles have a strong force of attraction between them, and the only movement that they make are tiny vibrations to and fro. This is why solids are rigid and retain their shape. If we take a stone and put it in a box, it retains its shape. Again, because of the small spaces between the particles, solids are not compressible. Liquids have no definite shape. In liquids, the particles are closely held together but are not in a fixed pattern. They move freely and have greater spaces between each other. Because of this space, the force of attraction between the particles is weaker than in solids. The spaces between the particles allow the liquids to be slightly compressible. In the gaseous state, the particles are far apart. There is a lot of space between them and move about randomly. Due to the large spaces between the particles, the force of attraction is negligible. The huge spaces between the particles make gases to be highly compressible. The three states of matter are interconvertible by changing the conditions of pressure or temperature. When a solid is heated, it changes to liquid. This is called melting. On further heating, a liquid vaporizes into a gas. This is called evaporation. Similarly, in the reverse process, gases on cooling change to liquids in a process called condensation. And on further cooling, the liquid changes into solid, a process called freezing. Now, related to the gaseous state is another state of matter called plasma. It is a state of matter that consists of a mass of free electrons and positively charged particles called cations mixed together. Plasma has no specific shape, no consistent volume. so it flows and takes the shape of any container, eventually filling it. Although the properties of plasma are similar to those of gases, plasma and gases are not the same thing. In plasma, electrons are released from the atoms, creating a pool of free electrons and charged ions called cations. Because the charged particles are loose, plasma easily conducts electricity and both produces and responds to magnetic fields. Plasma is created when a gas is either exposed to very high temperatures or when a high voltage electricity is passed through it. The heat or electricity makes the atoms in the gas move so quickly and collide violently with each other, and electrons are knocked out of the atoms. Because of the way they are created, plasma are sometimes called ionized gases. Although it is not as common as solids, liquids and gases, and was the last state of matter to be discovered, you're probably more familiar with plasma than you think. Plasma gives a neon or fluorescent lights that glow and is present in plasma screens. Scientists also classify fire as a plasma. Plasma makes up our sun and is visible in the solar flares that erupt from its surface. Another process that proves the particulate nature of matter is diffusion. Consider a bunch of rotting vegetables placed in a sealed container. The smelly gases from the vegetables will fill the container but will not be felt outside. However, when the lid is removed, the particles move out and spread to the entire room and can be smelled all over. The process through which the particles spread is called diffusion. It is the random movement of particles from a region of high concentration to a region of low concentration. Diffusion in liquids. We take some saturated solution of copper-2 sulfate in a beaker. With the pipette, we add some water to the solution of copper-2 sulfate carefully so that it forms a separate layer on top of the blue solution. We cover the beaker and leave it undisturbed. Initially, water flows on the surface of the copper-2 sulfate solution because it is less dense. After some time, the two are completely mixed and the blue color becomes pale. This happens because the particles of copper-2 sulfate intermingle with those of water. Diffusion in gases. Again, arrange a gas jar containing bromine gas and another containing air. Remove the cover plate. The brown color of the bromine gas rapidly spreads into the jar containing air to produce a uniform bromine-air mixture of pale brown color. Diffusion occurs because of the spaces between the particles and the random movement of these particles. It is faster in gases due to the large spaces and the high-speed random movement of these particles. It is slower in liquids due to lesser spaces and slow movement of particles. In solids, diffusion is negligible due to lack of spaces and very minimal movement of the particles. Different gases diffuse at different rates depending on the size of their particles. Consider this long glass tube open on both ends. We plug one end with a cotton wool soaked in ammonia and the other with a cotton wool soaked in hydrochloric acid. We seal the ends with rubber corks. After a short while, a ring of dense white fumes is formed. This is ammonium chloride formed when hydrogen chloride gas reacts with ammonia after meeting. The position of the fumes suggests that ammonia diffused faster than hydrogen chloride. We will deal with the rates of diffusion later in Form 3. And so, the key thing in this chapter is that matter is not continuous. it is particulate. In other words, it is made up of tiny particles. The particles have spaces between them. The particles are in constant motion, and the particles attract each other. Understanding this will help in explaining the behavior of matter as we proceed.